Welcome back. In this lesson, we are going to zoom in and focus on estimation and inference. A practical way you can think about this part of the curriculum is that you can't always look at the whole population of the thing you are trying to understand. Instead, we need to obtain information from a sample. Let me give you an example. You can't survey every wireless customer, every bond in an index, or every stock in a universe. You survey some of them. This video is about how you pick the sum and why that choice decides whether your answer means anything at all. By the end, you will be able to do three things. Compare and contrast 6 sampling methods: simple random, stratified random, cluster, systematic, convenience, and judgmental. Define sampling error and explain a subtle trap that shows up when you pool data from 2 different populations into one sample. This is the foundation underneath every survey, every backtest, and every performance comparison you'll ever run. Every hypothesis test you'll meet later in this course assumes your sample was drawn properly in the first place. Get the sampling wrong, and the fanciest test statistic in the world is just building on sand. There are 2 families of sampling. Probability sampling gives every member of the population an equal shot at being picked. Non-probability sampling doesn't, and that's exactly where representativeness breaks down. Simple random sampling is the baseline. Every element of the population has an equal probability of being selected. It works best when the population is fairly homogeneous, when one company or one data point looks broadly like the next. Whatever method you use, the sample statistic won't exactly equal the population parameter. That gap is called sampling error, the difference between what you observe in your sample and the true value you were trying to estimate. It exists because you looked at a subset, not the whole population. One more idea worth planting now, because a video later in this section builds directly on it. Every sample statistic, like a sample mean, is itself a random variable. It has its own distribution, called the sampling distribution. How tightly that distribution clusters around the true parameter is exactly what the central limit theorem lets you measure. A common mistake is assuming that sample statistics, for example the sample mean, are true, but in reality they come with estimation noise or uncertainty, and the sample statistic will have its own confidence interval. We'll cover this in more detail in the central limit theorem video. Stratified random sampling is designed for populations that are heterogeneous, that is, populations whose members differ in important ways. Rather than treating the entire population as one uniform group, stratified sampling divides it into smaller subgroups, known as strata. Each stratum is based on one or more relevant characteristics, and its members should be relatively homogeneous within that subgroup. Ideally, the strata are similar within themselves, but meaningfully different from one another. After the strata have been defined, a simple random sample is selected from each one. The number of observations drawn from each stratum is often proportional to that stratum's share of the total population. For example, if one stratum contains 20% of the population, it would typically receive about 20% of the total sample. The separate samples are then combined to produce an overall sample. The main advantage of this method is that every important subgroup is represented. A simple random sample drawn from the entire population could accidentally include too few observations from a small but significant subgroup. Stratification reduces this risk. When the observations within each stratum are genuinely similar, stratified sampling can also produce estimates with lower variance and greater precision than a simple random sample of the same size. Let's look at an example, because this is exactly how bond indexes get built. Bond index replication is a practical case. A broad bond index may contain thousands of securities, making it costly and sometimes impossible for a portfolio manager to purchase every bond in the index. Bonds also differ across several dimensions, including economic sector, time to maturity, credit quality, coupon rate, issuer, and liquidity. Because the index is heterogeneous, holding a small collection of bonds chosen without considering these differences may produce a portfolio whose risk and return do not closely match the index. Instead, the manager can divide the index into strata based on the characteristics that most strongly influence bond performance. Suppose the index is divided into 3 sectors, such as government, corporate, and securitized bonds, 6 maturity bands ranging from short-term to long-term, and 2 credit quality tiers, such as investment grade and lower quality bonds. Each combination of sector, maturity, and credit quality forms a separate stratum. The total number of possible strata is 3 times 6 times 2, which equals 36 strata. For example, short-term investment-grade corporate bonds would form one stratum, while long-term lower-quality corporate bonds would form another. To achieve full coverage, the sampled portfolio would need at least one suitable bond from each non-empty stratum. In practice, larger or more influential strata would usually receive several bonds, while smaller strata might receive only one. The manager would also consider each stratum's weight in the index. If medium-term investment-grade corporate bonds make up 12% of the index, the portfolio would generally allocate approximately 12% of its value to bonds from that stratum. The manager may then choose individual securities within the stratum based on liquidity, transaction costs, availability, and similarity to the stratum's overall characteristics. This approach is often called stratified sampling, or cellular replication, in bond index management. It does not attempt to hold every bond in the benchmark. Instead, it constructs a smaller, more manageable portfolio that preserves the benchmark's major sources of risk and return. If the strata are selected carefully, the portfolio can track the index closely while requiring fewer securities and incurring lower trading and administrative costs. It can still experience tracking error, though, because the sampled bonds won't behave exactly like every bond they represent. Cluster sampling may look similar to stratified sampling, because both methods divide a population into subgroups. But the two methods use those subgroups in almost opposite ways. In stratified sampling, the researcher draws observations from every subgroup to ensure that each important category is represented. In cluster sampling, the researcher randomly selects only some of the subgroups and collects data from those selected groups. The subgroups in cluster sampling are called clusters. They're often based on natural or convenient groupings, such as states, cities, schools, offices, households, or bank branches. Ideally, each cluster should resemble a small version of the overall population, reasonably heterogeneous within itself, containing a mixture of the different types of observations found in the full population. The clusters should also be broadly similar to one another. After dividing the population into clusters, the researcher can use one-stage or two-stage cluster sampling. In one-stage cluster sampling, a random selection of clusters is made, and every member of each selected cluster is included in the sample. In two-stage cluster sampling, a random selection of clusters is made first, followed by a random sample of individuals from within each selected cluster. Multi-stage cluster sampling adds further stages still. A researcher might select states, then cities within those states, and finally individuals within those cities. Consider a research firm that wants to measure investor sentiment across an entire country. Creating a complete national list of individual investors and randomly sampling from it could be costly and difficult. Investors are geographically dispersed, and contacting a sample spread across every state may require considerable time and resources. Instead, the firm could treat each state as a cluster. It would randomly select a manageable number of states and conduct its survey only within those states. If it selected 5 states and surveyed every investor in those states, that would be one-stage cluster sampling, and probably impractical because each state could contain hundreds of thousands of investors. A more realistic approach is two-stage cluster sampling. The firm first randomly selects several states, then randomly selects individual investors from each chosen state. It might select 8 states and survey 250 investors in each one, for a total sample of 2,000 investors. The main advantage of cluster sampling is efficiency. It can substantially reduce travel, data collection, and administrative costs, because the sample is concentrated in a limited number of locations or groups. It's particularly useful when a complete list of every individual in the population is unavailable, but a list of clusters is accessible. Its main disadvantage is that members of the same cluster often share characteristics or experiences. Investors living in the same state may be influenced by the same industries, local economy, tax rules, housing market, or political environment. As a result, 250 investors from one state may carry less independent information than 250 investors drawn from across the entire country. Cluster sampling can therefore produce greater sampling variance and lower precision than a simple random or well-designed stratified sample of the same size. The choice of clusters matters enormously. If the selected states aren't representative of the country, say, they happen to be dominated by similar industries, the survey may produce a misleading estimate of national investor sentiment. Researchers often address this by selecting more clusters, sampling fewer individuals within each one, and weighting the results to reflect differences in cluster size and selection probability. The central distinction is straightforward. Stratified sampling selects some observations from every subgroup to improve representation and precision. Cluster sampling selects only some subgroups to make data collection more practical and economical. The trade-off is important. Cluster sampling usually gives you less accuracy than stratified sampling because a sampled cluster might not perfectly represent the whole population. What you get in return is speed and cost, usually the most efficient way to sample a genuinely huge population. Here's the trap. Stratified sampling includes every stratum and samples within each one. Cluster sampling includes only some clusters, but once a cluster is chosen, you're drawing from inside it, not skipping it. Mix up which one guarantees full coverage and you'll misjudge exactly how representative your sample actually is. Systematic sampling is simpler still. Pick every KTH member of the population until you've got the sample size you want. Watch for hidden periodicity though. Say you sample every 7th transaction and your data happens to follow a weekly pattern. Every single pick lands on the same day of the week, and your random sample is really nothing of the sort. Now, the two non-probability methods. Convenience sampling means taking whatever data is easiest to access, a seasoned auditor's judgment call, or a database that's already open on your desk. Judgmental sampling means hand-picking elements using your own expertise, the way an experienced auditor flags the transactions most likely to contain a problem. Both are fast and cheap, and that's not always fatal. For a quick pilot study, it's a reasonable trade. But both carry a real risk of an unrepresentative, biased sample because neither one gives every element an equal chance. Now for the trap that catches even careful analysts. Sampling error isn't just about sample size. It's also about whether every observation in your sample actually comes from the same population. Say a fund manager runs a low-risk strategy in year 1 and a high-risk strategy in year 2. Year 1's quarterly excess returns, -4%, 8%, -4%, 8%. That's a 2% average with a standard deviation of about 6.93%. Year 2, -16, 32, -16, 32%, 4 times as wide, and 8% average, 27.71% standard deviation. Divide return by standard deviation, and you get the Sharpe ratio. Both years come out to about 0.29, comfortably ahead of a benchmark sitting at 0.27. Judged year by year, this manager beat the benchmark twice in a row. Now pool all 8 quarters into one sample, the way it might feel natural to do with more data. The average becomes 5%, and the standard deviation jumps to about 18.97%, because you've mixed 2 very different distributions together. The pooled Sharpe ratio drops to about 0.264 below the benchmark's 0.27. The larger sample didn't make the answer more reliable. It made it wrong because it wasn't sampling from one population anymore. The Sharpe ratio formula is worth memorizing. You'll see it again elsewhere in the Level 1 curriculum, particularly in portfolio management. The formula is Sharpe ratio equals portfolio return minus the risk-free rate divided by the standard deviation of portfolio returns. It measures the amount of excess return earned for each unit of total risk. Before you calculate it, though, make sure the return observations come from one consistent population, the same portfolio, time period, return frequency, and measurement method. For sampling methods, Focus on remembering the 6 main names: simple, random, systematic, stratified, cluster, convenience, and judgmental, and the feature that separates each pair. Simple random sampling selects observations entirely at random, while systematic sampling selects every kth observation. Stratified sampling draws from every subgroup, while cluster sampling selects only some whole groups. Convenience sampling chooses the easiest observations to access, while judgmental sampling relies on the researcher's expertise to pick observations considered representative. Here's one for you. An analyst pulls data from a database she already has open on her desk because it's what's there. A second analyst picks every 10th company from an alphabetical vendor list. A third analyst divides companies into 3 regions and randomly samples from each in proportion to each region's size. Name all 3 methods. The first is convenience sampling. She used it because it was already accessible, not because it was representative. The second is systematic sampling, a fixed interval, every 10th name. The third is stratified random sampling, divided by region, sampled proportionally within each group, then pooled. Let's recap the key ideas from this section. In probability sampling, every element has a known non-zero chance of selection, although those chances aren't necessarily equal. In non-probability sampling, selection probabilities are unknown, which leaves the sample more vulnerable to selection bias. Simple random sampling gives every element an equal chance of selection, and works best when the population is reasonably homogeneous. When meaningful differences exist, stratified sampling divides the population into relatively homogeneous strata and samples from everyone dies, guaranteeing representation of important subgroups and often improving precision. Cluster sampling also divides the population into groups, but randomly selects only some clusters. Researchers then survey everyone in the selected clusters, or take a further sample within them. This reduces cost and collection time, although similarities among members of the same cluster can reduce precision. Systematic sampling selects every kth element after a random starting point, but check first that the ordering of the population doesn't contain a recurring pattern that coincides with key. Whatever method you use, the observations should come from the same clearly defined target population. Combining data from populations with different characteristics or distributions can hide important differences and produce misleading results. A larger pooled sample isn't automatically better. If its observations don't represent one coherent population, it can be less trustworthy than a smaller, carefully selected one. Next up in quantitative methods, the central limit theorem and the use of resampling to estimate the sampling distribution of a statistic. These are the second half of the estimation and inference material. See you in the next one.